I'm back working on the Z80 computer project, and in this video I want to start working on the operating system. So initially I'll be trying to get this to boot to CP/M, so that's what we'll be working on today. I've been through the board and thoroughly tested it. It's working very well, haven't found any real issues with it. The only design change I'm going to make in the next revision is this wire link you can see here. Now it's connected to pin 1 of this device, and this is an 8-bit latch, and that latch is the one that controls the DMA circuit and also the floppy drive interface. So the Z80 just sends it a value that puts the DMA and floppy drive controller into a certain mode. For example, if we want to select disk 1, 2, 3 or 4, or use single density, double density, that sort of thing, and that latch controls that. Now I was initially using a 74LS374, and this, as I say, it's just an 8-bit latch, and pin 1 on the 374 is the output enable pin, but because the outputs are enabled all the time, that pin was permanently tied to the rail. But I decided that, especially because I'm developing the system and the software, there's a risk that when you boot up the machine, the output of those latch pins could be in any undefined state and put the circuits into a mode we might not want to use. Shouldn't do any damage, but just to be on the safe side, I've made this change now. One of the first things the boot ROM does when we boot or reset the machine is it explicitly sets that latch, so it sends a value to it to deselect everything. But of course, especially when developing the software, there's a risk that the system might not boot up properly. So I've swapped the 374 with a 74LS273. Now that's an identical device. The only difference is pin 1 on the 273 is an asynchronous reset pin, and it's active low, so it is of course just now connected to the Z80 reset line. So whenever we reset the machine or boot the machine up, the latch will come up into a known state. It'll work fine with the 374, but I've just done this as a kind of belt and braces approach to make sure I don't do any damage to anything. If you do build one of these, you can fit either device. It will work fine with both. Now, as I said, what I want to do in this video is start work on CP/M. I won't get it all done in one video, of course. It's quite a big job to get CP/M running on a machine like this. It's relatively straightforward in concept, but there are some complications that I'll need to work around to get it to run properly on this particular machine. So we'll start off by having a look at the general layout, and if you're not familiar with CP/M, it's a very simple operating system designed for small computer systems like this, very popular back in the day, and the designers of it were very forward thinking and made an excellent job of putting it together, and they put it into, or designed it in, 3 major parts. There's the CCP. I've got this diagram here, a very rough sketch of this machine layout and how we're going to approach this. So CP/M in this case consists of CCP, that's the command processor module within the system, BDOS, which controls all the in-out operations for our devices, and all CP/M really does is allows us to save and recover data to floppy disks in a file format to make things much more straightforward, and it also allows us to control some simple in-out devices. The first 2 parts, CCP and BDOS, are fairly standard within CP/M and normally, quite often, don't need much change. I will need to modify them for this machine. I'll explain why later on. The main part that normally has to be modified or written by the designer of the machine is the BIOS, not to be confused with the boot ROM. The boot ROM code is completely separate. CP/M can of course be put into a ROM, but it's not necessarily going to be in a boot ROM. So the 3 parts, CCP, BDOS and the BIOS, need to be tailored for this machine, and then they need to be loaded into the machine when we boot it up. Now, I demonstrated a few videos back in this series the bootload process and the first stage and second stage bootloaders, and I will ultimately be putting CP/M onto a floppy disk that we can boot from. But for test purposes, what I'm doing is I'm using the serial port to develop the system the same way I have for other software that I've demonstrated on this. Just to clarify, the serial port is not used for our display. This serial port does not go to this display. This is not a terminal. This is just a CRT in a case. There's nothing else in there. It's just being driven directly from our Z80 board. And that's one of the reasons we have a complication, which, as I said, I'll come back to later when we design the BIOS and the CCP for this particular machine. When CP/M starts up, it has to initialize some values at the bottom of RAM, and that means that it can't run from, in our case, bank 1, because at the bottom of bank 1 we have our boot ROM, which is this device over here. So when we boot this machine, it branches to the bottom of bank 1, starts executing the code in the boot ROM, and that contains, amongst other things, our bootloader and also the monitor that we have. So press the key, the monitor comes up, and that's running from the boot ROM. Now, when we load CP/M, the general idea will be we will load a second stage bootloader. I'll be skipping that in this video because I'm loading the software directly through the serial port, but normally this second stage bootloader will be taken from the floppy disk by the first stage bootloader in the boot ROM. It's then handed control, and its function is to get CP/M from the floppy disk and load it into RAM. When CP/M starts up, one of the first things it does is to initialize the values in the bottom of RAM, and we'll know fairly quickly if this is working, because if it's not, we won't be able to make any calls to CCP and BDOS, and hence the BIOS, because it won't be able to branch to the correct address. If you're familiar with CP/M, obviously you're going to know all this, but essentially there's an address that's stored right at the bottom of RAM that's used to call the functions within the BIOS, and that's initialized as part of the startup for CP/M, and if it's not right, we won't be able to call any of the functions. So the general layout for this machine, bank 1, we have the boot ROM at the bottom. Now at the top, this is shared RAM, so it's common across both banks. Right at the top we have the non-volatile RAM. Below that we have the video RAM. Below that we have the monitor stack, the interrupt vector tables, and some system variables in RAM that the monitor uses. And we will be loading CP/M just below that. To get CP/M to start up, it has to be loaded into bank 0, and then we have to switch banks to bank 0 so that CP/M can run. It can't run from bank 1. And then user programs are put into the remaining RAM above the CP/M work RAM area and below CP/M itself. So quite a complex task to get this put together, but the first things we'll need to do are start developing the software. So I normally start with some fairly standard files for CP/M. Over the years I've probably written 10 or 12 different versions of it for different machines, but this is the first time I've ever written one for a totally new machine, so it should be quite a fun project. So we'll go over to the PC, have a look at the code and how I'm going to modify it, and then we'll go from there. Try and get CP/M to boot up in this video, but it will be very minimal boot, if at all. Chances are the system will just crash, but we'll give it a go. And as I say, I'll go over to the PC now and explain the initial changes I'll be making to CP/M to try and get it onto this machine. So over at the PC, I've spent several hours already working on this. I started with the basic image and source code that I have for CPM. That's the CCP and the BDOS. I appended to the end of that the skeletal BIOS that's provided by Digital Research. Now really it's aimed at 8-inch drives, so I've needed to make a few changes, and also I've added some extra functions already, which I'll explain now. As I said, I've been working on this for probably 2 hours, but there's quite a lot of work left to do, probably several days work to get it working properly, but in this video I just want to get it to boot up, hopefully to the CPM command prompt, and we'll go from there. So the first thing we do is define where in RAM the CPM is going to be copied to. Now in this case I've declared it as a 62K memory space, because as I just showed with the diagram, we have our video RAM at the top of the RAM space, and so I've allowed space for that, and we'll install CPM just below that. And so this value, this calculation, determines where in RAM we start copying the data to. So that's right at the bottom of the CCP in the CPM stack, and in this case it works out to be D800 hex. We then initialize some values. Most of this is standard, it's just directly from the CPM source code unchanged. Where it starts getting different is I've added some equates for our particular floppy drive control system and some of the other code that we're going to need to add. There's quite a few of these, but this just makes it easier to understand the code later on. We then have these values. Now these are what are used by the monitor program, and these are initialized by the boot up ROM, and these are here just in case we want to make use of them later on. The one we'll definitely need is the interrupt table, because we do need to update the vector for the keyboard interrupt handler, and we need to use the handler for the keyboard because it's a PS2 keyboard and each key press actually returns 3 values, or at least 3 values, and we need to interpret the codes coming from the PS2 interface, and hence we also have a lookup table for doing that. So I'll come back to that in a few minutes, but it is just convenient for us to use the same interrupt table. We're not going to overwrite it with CPM, so we might as well just update the value for the PS2 vector. Also the other vectors are still intact as well, so if we want to make use of those in CPM we can. Now this comes back to why I developed the DMA system before starting this, because I want to have the keyboard running using an interrupt and the floppy drive interface using DMA, and that means that during a floppy disk read or write the interrupt and the Z80 can be doing other things, so it's very efficient in terms of the operation of the Z80. This part is just for debugging. This is because of the way this simulator works, but it's not really part of the code that ends up on the Z80 machine. So we start from here. The base is the address that we just looked at, so this is the address D800, and that's where we will copy the code to, and this is the start of CCP. And I've put the CCP labels here just because we need these later on in the code to figure out where to jump to. So the first thing we do when CPM starts up is we switch to bank 0. Now this will normally be done at the beginning of the second stage bootloader. It doesn't need to be, we can do it here, but it's just easier, and it will take less shared RAM to start up the system. But we switch to bank 0. We then update the keyboard interrupt handler vector in the interrupt table to point to the interrupt handler for the keyboard that's in this code, as opposed to the one that's in the ROM, the boot ROM, because of course we no longer have access to that boot ROM code. And then we jump to the CPM boot, again standard call, and this just initializes a few things, including the values at the bottom of RAM, and then it branches back to here, so I won't bother showing you that. That's the standard in CPM. I haven't really changed that. The next thing it does is we have the usual copyright notice, etc. So most of what follows at the beginning of this code is fairly standard CPM. Now I will need to modify some of it. For example, CPM expects to be talking to consoles, things like dumb terminals and that sort of thing, paper tape punches. And because of that, it actually prints characters such as the character return and new line, because they're interpreted by the dumb terminal. So for example, if CPM wants to jump to the next line, at the beginning of the next line, then what it does, it prints to the console a character return and new line. Now we can't do that with our machine because the video system will simply print those characters on screen as odd characters, and I haven't modified that, so chances are if this does start up we'll see some odd characters on screen when we press the return key. But I can modify that and just have it interpret the character return and new line in the same way that the code does in the boot ROM. So when we run the monitor, for example, the monitor program is responsible for scrolling the screen, new line, that sort of thing, and we'll implement that same type of code in CPM for this system. So this goes through, and it's really standard CPM. If you're interested in this and you haven't seen it before, then there are plenty of online resources that explain how CPM works. So where it starts getting interesting is when we get to the BIOS. That's where we'll be doing most of our development work. So that starts here. Now, to get into the BIOS, which is really a collection of functions, we have this lookup table, a jump table. So each of these functions is accessed by calling this address with an offset. So for example, calling this address with a 0 offset, it will jump to boot function. Calling it with an offset of 2 will jump to this function, etc. So in this way we can standardize the function calls, and what we have to do is populate each of the functions. So if we scroll down to the first one, so the boot function starts here, and this just initializes a couple of values. Again, this is the skeletal BIOS. I haven't changed much of this yet, but we will have to change quite a lot of it for our system. But the first thing it does, it initializes the in-out byte, and I will be implementing the in-out byte mechanism. I'll explain what that is in a future video. By the way, if you want me to go into any more of this in more detail, then please leave a comment. But once it's initialized a couple of values, it jumps to the CPM initialization, which is here, and this is where the values at the bottom of RAM are initialized. Normally the interrupts are enabled here, but that was done back in the boot ROM, so we don't need to do it again here. I will tidy this code up once I've got it all up and running. And this then jumps back to CCP as I showed earlier, and that's where we jump to the command interpreter. It starts looking for commands entered by the user. In fact, before it does that, it tries to read the directory track off the floppy disk that's inserted, and it makes a record of any files it finds there. So if we can get this to boot, then we'll notice it accesses the floppy drive, even though we're not booting from floppy drive at the moment. So the functions I've changed so far are the console character output, and it does this in a similar manner to the boot ROM code. It's just simplified here because a lot of the donkey work is being taken care of by CPM. We have a console in, and this does a similar kind of thing to the monitor ROM. These are all commented out, so it's just a few lines, and the reason this is so easy to implement is because we're using an interrupt handler to read the characters from the keyboard, and we'll have a look at that in a few seconds. We also have other small changes to the functions as well, such as keeping track of the cursor position, but like I said, we'll need to modify this. Actually, we'll need to modify part of the CCP to keep track of where the cursor is on our particular implementation, because we can't just rely on the carriage return and new lines. Okay, so we then come down, all these I'll be implementing, the punch, the reader, all this sort of thing, but I haven't touched these yet. But where we get to the main changes I've made so far are in the floppy disk read function. Haven't touched the write yet, I don't want it writing to the disk just yet. And again, some of these lines are for debugging purposes, so you can ignore them. Others I've just temporarily commented out, so selecting different drives, etc. I will re-implement this once we get the system up and running. I've just simplified it at the moment to minimize the chances of anything going wrong. We use the DMA address that's part of CPM, and that address changes depending on what CPM is doing. But we use that and we load that into our DMA counter. We normally should take care of homing the drive, but because I want to be able to accurately debug this setup as I'm developing it, the drive, if it's accessed, will be accessed one sector at a time, and then it will be deselected, so we'll hear the drive clunking away each time the sector read function is called, basically this function. So for example, if it does get as far as trying to read the directory track on the disk, when we try and boot up CPM, you'll hear the drive clunking away a few times while it reads each sector. But the rest of this is similar to what we saw in the demonstration programs I showed in previous videos, just simplified here because it's easier for us to implement this within CPM. And so it's using DMA. It tries to read the sector from the floppy disk into the CPM memory buffer, and again the side select code has been commented out. Normally this would be used to select which side of the floppy disk we're talking to. I will also be implementing support for both single density and double density. At the moment I've just implemented this and it's set up to use single density disks, and so I'll come back and add support for double density once the system's up and running. Okay, so as I say, deselects the drive each time it reads the sector, and that's so that I can keep track of how many times it's trying to access a sector. I haven't tried to run this yet, I'm not quite sure what it's going to do. This is the original code, which shows none of it's being used anymore. Got a couple of extra functions here for a few delays that I need. Haven't touched the write function yet. That'll be very similar to this, just using a write command of course instead of a read, and taking the data from the same CPM buffer. We've then got the keyboard interrupt handler. So we've updated the vector table and the entry for the keyboard interrupt to point to this particular function. So whenever we get a keyboard interrupt, we'll end up here, and this can run at the same time that floppy disks are being written to or read from. So similar to the code you've seen before, the only real difference is we don't need it to handle the cursor keys. In the monitor program we need this function to take care of moving the cursor around, but we don't need that here because that's done by CPM. So all these lines are commented out. I'll remove them once I'm certain the system is working properly. So it's a much more straightforward interrupt handler, and it just ends up putting the required key character into the CPM character buffer rather than the buffer we use within the monitor. It could update both, but here I think we're only going to need the character buffer for CPM. And the various flags etc. are to handle the multiple calls to this handler. As each key is pressed, it will generate at least 3 interrupts each time a key is pressed. And we need to make sure that we extract the correct character. And also it's using a lookup table to interpret the character and return it as an ASCII value, and that table is here. And the rest of it is the same. So as you can see, I haven't made many changes yet. I've just tried to get the general framework set up so we can do some basic testing. And so what we can do now is try to compile this. Okay, so we've ended up with hopefully an object file that we can send to the Z80 computer. So we'll go back to the Z80 and we'll try and send the program we've just compiled to the Z80 and see if it actually does anything. Okay, so back at the Z80, I'll just dim the lights a bit so hopefully we can cut down on the flicker. What we've got here is the machine setup. We don't have anything loaded into it yet other than it's just booted into the monitor, and if you recall we have a function that will allow us to load a program from the PC through the serial port. The address we want for this, if you recall from the start of the CPM code, is D800, and it's now waiting for a file. So I'll go and send the file from the PC and hopefully that will be successfully loaded into RAM at the correct address. So that's loaded into RAM, we hope, so we'll just examine that and make sure it is actually there. So D800, we should see the code. And hopefully you can see this, we're seeing the copyright notice is at the beginning of the code, so it does appear to have been successfully loaded. Haven't tried running this yet, so it should be fun to see what happens. What I've got here is a floppy disk that's been formatted using the utility I've shown previously. It's been formatted in single density mode, 128 bytes per sector. That's the data payload, not the entire sector size. But this should be readable by the system that we have here now. Now I haven't done any tidying up of the code, so it's not going to clear the screen or show us the sign-on message, anything like that. It's just simply going to try and boot from the image we have in RAM, and if it's working then one of the first things it should do is to try and read the directory track from the floppy disk. So we'll just clear the screen just to make it a bit easier to see what's going on, and we'll try jumping to the CPM startup and see what happens. This normally would be done by the second stage bootloader once it's finished loading the code, and it will in theory do exactly the same thing it's doing now, but let's see what happens. It's going to switch to bank 0 and try and run CPM, so let's see what it actually does. So you can hear, as I said, it deselects the drive after each sector read, and we've even got the CPM prompt. I don't know if you can see that right at the top of the screen, just trying to see it through the viewfinder on the camera. So we have the actual CPM prompt, which is quite surprising, but we don't know if CPM is really running yet, but it certainly seems to have done the right thing. Now if CPM is running, it has some built-in commands, and one of those is the directory command. That's dir, and if I type dir then we should hear the drive being accessed. It's probably pushing our luck a bit trying this, but okay, so the keyboard interrupt system is working, it's reading the correct keys. We can enter it in lowercase, by the way. CPM does translate commands to uppercase before it tries to execute them. So now I can press the enter key. Now we will get odd characters. Like I said, it's not interpreting the carriage return that the way the terminal would. So it's not going to go to the next line, it's going to actually show the character on screen, but it will correctly enter it as a command, assuming that CPM is correctly reading the command. So we'll try this. Okay, and it's saying no file. And going back to the command prompt, which is exactly what it should do. This is a formatted disk, there are no files on it, so it is doing the right thing. It's saying no file. The J, if you can see it, there's a J at the end of the just after no file, and I believe that is the character it shows on screen whenever we press the enter key, which it is. You can see each time I press this we get that same character showing on the screen. Now if we enter something that's a non-command, so just enter a few random characters and then I'll press enter, we should get a CPM repeating that with a question mark at the end, which it is doing, so that's very good. It means that it seems to be actually running. It's tried to access the disk, it's realised it doesn't have either an inbuilt command with that name or a file available on the floppy disk with that name, so it's just basically coming back saying, don't know what you mean. We'll try something else and just see if it's still going. And it is, and as you can see it's translated it to uppercase and put a question mark at the end, and as I said, the J's are just the carriage return character being printed. I'll stop it doing that and just have it not print these particular characters. They are of course being correctly interpreted within CPM, which is why it's trying to execute the command. We'll try the dir one more time and say no file, which is correct. What we can do now is take this disk out, and one of the things I always say when developing systems, it's as important they can detect errors as work properly when things are going right. So what I've got now is a disk it is formatted, but it's formatted in double density, so this current version of CPM should not be able to read this. So if I try doing something similar and hitting the dir key, we should get an error. And we're getting BDOS error on A, bad sector, which is exactly what it should do. It means it's successfully tried to read the disk. It's come back saying it can't read that disk, there's something wrong with it, which is what it should do. It's not properly formatted for this particular machine now. And we'll just put the original properly formatted disk back in and see if that works. And it's saying no file. So okay, it's kind of surprised me a bit. We've got a lot further than I expected to. CPM is actually now running on this machine. It's limping along. It needs obviously a lot of work doing. It needs the right function implementing so we can write data back to the floppy disk, and then we can try creating a file on the disk and see if it's properly handling the various features required to handle the files. But certainly it seems to be doing what it's supposed to. It's successfully switched to bank 0, started up CPM, it's accessing the disk the way it should, it's coming back with the correct responses, it's recognizing disks that are not properly formatted, and it hasn't crashed, so that's a good sign. As you can see, I need to do a lot of tidying up of the display, get the rest of the functions within CPM working, but this is a very good first step, and it should be a lot of fun trying to get CPM to work properly. Once it's up and running properly, I'll copy the CPM software to a floppy disk, write a second stage bootloader that will load CPM into RAM. It'll be very similar to the second stage bootloader I showed before. It will just load multiple sectors to a different address. And it should be interesting to see how well CPM runs on this machine, but it's certainly looking very promising so far.